Hello everyone. Let's start the chapter 1. It is the introduction chapter to physics. Now, physics is a quantitative science based on careful measurements of quantities such as mass, length, and time. First, I would like to introduce the learning objectives for this chapter. So at the end of this lecture, you will know how to determine the correct number of significant figures in a problem and convert a quantity from one unit of measure to another, for example, millimeters to meters or grams to kilograms, and to correctly perform unit algebra. That means you will be able to determine the units of a final result by multiplying and dividing units. Finally, you will have a better understanding of the scalar and vector quantities. You will be able to explain the difference between scalars and vectors. Now, this is the chapter outline which I will going to cover throughout this chapter. Let's discuss each of these one by one. First, what is physics? We are going to study physics throughout this lecture series. So first, we need to know what is physics. Physics is the basic study of the fundamental laws of nature, the laws that underline all physical phenomena in the universe. Remarkably, we have found that these laws can be expressed in terms of mathematical equations. So what makes physics particularly fascinating is the fact that it relates to everything in the universe. Interestingly, all this complexity and variety that we see in the world around us and in the universe are manifestations of a few fundamental laws and principles in physics. So physics combines both theory and experiment in the study of the law of nature. So to make comparison between the laws of physics and our experiences in the world, we need to know how to measure some certain basic physical quantities. So the most common of these quantities are length, mass, and time. We begin by defining these units of these quantities. The SI unit of length is in meters and the unit symbol is m. SI unit of mass is in kilograms and the unit symbol is kg. SI unit of time is in second, unit symbol is s. So all these units symbols are in lowercase, but there are some unit symbols in uppercase which we will be learning in our next chapters. These units we call as SI units, which are the global standards. So when we solve an equations, always try to convert all the units into SI units. But there is another system of units similar to this system. We call this system as MKS, and the next system is CGS system. In this system, we express length in centimeter, mass in grams, and times in seconds. But one thing to notice is that when we solve an equations, we need to convert all the units into the SI units, that means to MKS system. Now, multiples of the basic units are common no matter which system is used. So standard prefixes are used to designate common multiples in powers of 10. So the most common prefixes are listed in this table. 10 to the power 15 is peta and the abbreviation is P. 10 to the power 12 is tera, abbreviation is T. Likewise, you can go through this table. For example, the prefix kilo is 10 to the power 3 and the symbol is K. That means 1000 or equivalently 10 to the power 3. Because of that, we can say 1 kilogram is equal to 10 to the power 3 grams, or 1 kilometer is equal to 10 to the power 3 meters. Why? Kilo is 10 to the power 3. Similarly, let's look at another example, milli. Milli is 10 to the power minus 3. So we can say 1 millimeter is equal to 10 to the power minus 3 meters. Likewise. Now let's see some examples of unit conversions. A baseball has a diameter of 75 millimeters. And can you give the diameter in meters and kilometers? Here the standard unit for measuring length is in meters. So let's first convert millimeter to meter. So 75 millimeters means mm. It is equal to, milli means 10 to the power minus 3. So it is 75 times 10 to the power minus 3 meters. Or we can write it as 0.075 meters. Now we need to convert this number into kilometers. Now what is kilo? That means 10 to the power 3. We know 1 k is 10 to the power 3 from our prefix table. So 75 millimeter, we convert it to meters. That means 10 to the power minus 3 meters. And to convert it to kilometers, we need to multiply by 10 to the power minus 3. Then we get this unit kilometer. Why? 1 kilo is 10 to the power 3. So 1 is 10 to the power minus 3 kilos. So because of that, we have to multiply by 10 to the power minus 3. And we can get it as 0.00075 kilometers. Now let's see one more example. A house sells for $450,000. Can you express the price of this house in kilo dollars and mega dollars? Can you give a try? So $450,000. This is equal to 450 times 10 to the power 3 dollars. And we have to express this in kilo dollars. We know 1 kilo is 10 to the power 3. So instead of this 10 to the power 3, we can write it kilo. So it is 450 kilo dollars. Now we have to convert it into mega dollars. So what is mega? 1 mega is, you can check the table, it is equal to 10 to the power 6. So we can write $4,050 as 0.450 times 10 to the power 6 dollars. Is the same as $450,000. And now 10 to the power 6 means mega. So this is 0.450 mega dollars. Right. Now let's move to the next section. So in physics, when we speak of the dimension of a physical quantity, we refer to the type of quantity in question, regardless of the units used in the measurement. For example, a distance measured in meters and another distance measured in light years, but both have the same dimension, length. Now, any valid formula in physics must be dimensionally consistent. That is, each term in the questions must have the same dimension. To check the dimensional consistency of an equation, it's convenient to introduce a special notation for the dimension of a quantity. We will use square brackets for this purpose. So the dimension of some common physical quantities are listed in this table. So if x represents a distance which has a dimension of length in square brackets. So we can write x is equal to square bracket L. Similarly, area means two lengths, right? So it is L times L or L square. And let's look at another example. Velocity. Velocity has a dimension of length per time. Thus we can write V equals length over t. And for acceleration, which is the change in velocity per time, has the dimension of velocity over time. So acceleration has the dimension of velocity over time. So velocity is L over t, and over time means another t. So it is L over t squared. Now let's look at another example. So this is a simple example of analyzing dimension. Show that x is equal to x naught plus vt is dimensionally consistent. The quantities x and x naught are distance, and v is velocity and t is time. So how can we convert this into dimensional units? So x is equal to x naught plus vt, and x is a distance or a length. We can use square bracket L. Is equal to L naught is again a length, it is L, and v is velocity, it is length divided by time, L over t, and t is just t. Now this one and this t cancels out, and we get L plus L in the right hand side. So because of that, we can say that each term of this formula has same dimension L. So this type of calculation with dimension is referred to as dimensional analysis. So dimensions obey the same rules of algebra as other quantities, as we can cancel t in here. Since each term of this formula has same dimension L, we can say that this equation is dimensionally consistent. So if you are given to find an equation whether it is a dimensional consistent, you need to check each term of the equation and write in the square brackets of length and time. Okay, so let's move to the next section of this chapter. In this section, we discuss a few important characters of numerical values. First one is the significant figures, which defines as the number of digits in a quantity that is known with certainty. We know that every measurement has some degree of uncertainty. That means we don't know how accurate the measurement is. For example, the least number we can measure from a ruler is 1 millimeter, and we can't measure smaller lengths than 1 millimeter from a ruler. Therefore, the accuracy of measurement is limited. For the case of ruler, it is limited to 1 millimeter. Suppose you measure the distance traveled by your pet tortoise from a ruler, and you find the distance is 21.4 centimeter. So each of these 3 digits is known with certainty. Therefore, we can say D has 3 significant figures. If the distance is 21.4 centimeter, we can say D has 3 significant figures. But if you measure this distance from another instrument like a vernier caliper, which has an accuracy of 0.01 centimeter, you can measure up to 2 decimal points. It is 0.01 centimeter, and you can measure up to 2 decimal points. Therefore, that measurement is more accurate than the measurement from the ruler, because this has only 1 decimal point. Therefore, we can say that the greater the number of significant figures, the more accurately the quantity is known. There are some rules applied to significant figures. The first one is the number of significant figures after multiplication or division is equal to the number of significant figures in the least accurately known quantities. For example, if our tortoise traveled the distance 21.4 centimeter in 8.5 seconds, so it traveled the distance 21.4 centimeters in t is equal to 8.5 seconds. T is equal to 8.5 seconds. So we can determine the speed of the tortoise by dividing the distance over time. So the speed is distance over time. It is 21.4 centimeter over 8.5 seconds. Or the answer is 2.51764770. So clearly such an accurate value for the speed is unjustified, considering the limitations of our measurements, because D has only 3 significant figures and T has only 2 significant figures. So we need to apply the significant figure rule to determine the number of significant figures in the final answer. Therefore, according to the rule, final answer should have the least number of significant figures. That means 2, because T has only 2 significant figures, and whereas the distance has 3. So the least number is 2. Because of that, the answer should have only 2 significant figures. So this is not correct. The answer should be 2.5 centimeters per second. Right? Now, the next rule applies when adding or subtracting 2 numerical values. So that is the number of decimal places after addition or subtraction is equal to the smaller number of decimal places in any of the individual terms. Let's see an example. Okay. For example, suppose you are doing the time measurement for a race. So if you make a time measurement of 16.74 seconds, 16.74 seconds, that is one time measurement T1. .74 second, and then a subsequent time measurement of 5.1 second. You do another time measurement of 5.1 second. So how many significant figures in T1? It's 4, and for T2 it has 2 significant figures. Now the total time for the two measurements. What is the total time for the two measurements? T1 equals T2 is equal to 16.74 seconds plus 5.1 second. The answer is 21.84 seconds. So now the answer is correct or not. So according to the rule, the answer should have the smallest number of decimal places. That means the first number has 2 decimal places, the second number has 1 decimal places. So the answer should have only 1 decimal place. So this is not correct. The answer should have 21.8 second. Only 1 decimal place. So that's the rule applied for adding and subtracting. Let's look at another example. I will clear the pen markings. So there's a race between a rabbit and a tortoise, as shown in the sketch. So the rabbit pauses to eat a carrot while the tortoise walks at a constant speed. The tortoise travels at a constant speed of 2.51 centimeters per second for 12.27 seconds. Now you are asked to find the distance the tortoise go. So distance is speed times time. So here we can find the distance d. We have given the speed 2.51 centimeters per second times 12.27 second. So now the answer is 30.7977 centimeter. So the quantity that is known with least accuracy is the speed, because it has only 3 significant figures, whereas time has 4 significant figures. So the quantity with least accuracy has 3 significant figures. Because of that, we give the result with 3 significant figures. So the answer should be 30.8 centimeter. Because this is 79, we round up the values to 8. If it is beyond 5, we add one number when rounding up. We will discuss about the rounding up in our next sections. Okay. So D is 30.8 centimeter. I will erase this. And this is round out to 30.8 centimeter. Okay, let's see another example. You and a friend go fishing, suppose. So you catch a fish that weighs 10.7 lb and your friend catches another fish that weighs 8.35 lb. What is the combined weight of the two fish? So we asked to find the combined weight of the two fish. The fish you caught is 10.7 lb and your friend's fish is 8.35 lb. So the combined weight is 19.05 lb. So this has two decimals, and we will have two decimals in the answers. So according to the rule of thumb, the final result must have only one decimal place.